Hello to our video number 17. This is a video that's similar to infiltration. It's not really fertigation, but really most of the people who fertigate also have drip systems. That's the reality of it, at least in California. And they have to inject chemicals for drip system maintenance. So here we are in video 17. If you recall, go to our website and you get to free downloads, and in the free download section there are all sorts of resources that you can obtain, including the fertigation book in either Spanish or English. Plus we have the other lectures and lab exercise videos available on our website. So with drip irrigation, drip micro irrigation, there are two distinct plugging causes that can be addressed. One is bacterial growth inside the hoses and emitters, and it grows there and then can slough off. In the case of in hoses, it can eventually block the emitter pathways. So this is not algae, which grows from the outside and then is introduced to the pumps. This is bacterial growth. And there are all types of bacteria that can cause a problem. The second one is chemical precipitation in the emitters. We also have, and I'll address it briefly, we have root intrusion that comes in from outside. As usual, there are two ways people approach these problems. One is they believe in miracles, and so they just don't even notice anything until they have real serious problems. Often they're completely plugged emitters. And the thing is that some people really recognize that as a problem. What's more complicated is that all that time, it's not just the plugged emitter, but it's the partially plugged emitters that are really ruining their distribution uniformity, and that's not so obvious. So this is what we call rehabilitation, and where, boy, everything's messed up, and so somehow you have to improve things and get them better. That's a little tough sometimes, by the way. Another approach is they continuously or very frequently apply appropriate chemicals to avoid problems. You use specific chemicals for specific problems. And this is called prevention or continuous maintenance. And, you know, industries work this way, farming works this way. You know, what are you going to do? You have a choice here. Now, chlorine is one of the common chemicals used to kill bacteria growth. If you look, I'm going to shift my head here, and you can see, oops, wrong way or that way. You can see the blue container in the background on a reservoir. That's actually an installation where they are using tablets of chlorine, and they're injecting chlorine into the reservoir to help control bacteria. It's going to go into the drip system is what it is. Anyway, these bacteria, a lot of the bacteria, not all of them, but a lot of the bacteria that we have are slimy. And so what happens, if you recall, filters will go down to 160 mesh, 180 mesh, 200 mesh. It can be very fine, but filters that we use in drip irrigation were never designed to bring the water to drinking water quality standards. In other words, all the clay goes right on through. You may think the clay is being caught because it looks that way, but the clay particles are so small they go right through a 200 mesh filter. So those are tooting along down in the hoses and the emitters, and there's this slime in there, and obviously they adhere to the slime and they get bigger particles, and it builds up over time. Now, to be certain here, regarding chemistry, chloride, that's Cl with a negative, it's common in irrigation water, isn't going to do anything for your bacteria control because it's not chlorine. Chloride is found in most water. Table salt is sodium chloride, but again, it does not kill bacteria. I'm talking about chlorine here, and there are a couple of forms of chlorine, which I'll discuss. Almost everybody knows about bleach that use in laundry, and there is chlorine in bleach, and it's a specific form. If you notice the formula here, NaOCl. is called sodium hypochlorite. So the hypochlorite is the OCl. It has a negative charge. Now, bleach is fairly dilute, and you can buy containers, large containers of bleach solutions, sodium hypochlorite. One of the problems with that is it loses potency after a few weeks. So we used to use it when we were first starting out with drip, but it's rarely used anymore. We use other things like gas or pellets or something like that. And it's historically used on really small drip systems that homeowners use, and you can buy bleach, but it's not really used much at all in production ag. Now, if you remember from the previous slide, bleach is sodium hypochlorite, NaOCl. And there were some problems such as it degrades over time, but also it's a weak form of chlorine in terms of bacterial killing properties. You can convert that, like many things are pH dependent. You can convert it to hypochlorous acid. Let's see, how would you do that? Well, somehow you would get a lot of hydrogen ions in there. In other words, you acidify the water, and you take it from the right-hand side of this equation where you have the hypochlorite, you add some acid to it, and it makes hypochlorous acid. The good thing about that is it's about 20 times more powerful than the hypochlorite form. And this is one of the reasons when you talk with farmers, many of them will put chlorine into very high pH water, and they notice it doesn't do much. Well, yes, this explains it. They have to acidify the water at the same time they're putting the chlorine in to get it into a more potent form. So again, here's the bottom line when you use chlorine, if you want to use chlorine, and keep the rates down. And keep in mind that if the hypochlorous acid is 20 times more powerful, that means you only need to put 1/20th the amount in also if you drop the pH. So you drop the pH down to about 6.5, 7, which is really great for plants and nutrition, and it's much more effective. Most chlorine is applied either as gas, that's the upper right hand picture there. You have the large gas tank. That's all provided by commercial companies. Your employees don't touch it. They shouldn't be touching it. They set it up. It automatically works. Automatically shuts off if the irrigation system shuts off. Or on the upper left-hand side, you have set up, doesn't show all the details, but you can see there's something going into a chamber, and there's some pipes coming out, and those are tablets. Now, you do find strange things or unusual things. For example, in some places, nobody wants, or there are even regulations against chlorine gas. In that case, of course, you can take the tablet option. Now, remember I said there are two ways to handle things. One is regular maintenance, and another one is rehabilitation. And this slug dosage thing has been around for years. It's been in books. You can find it referenced in a lot of places where you can slug chlorine in. Sometimes the recommendation is even 200 parts per million. That's really risky, and it's risky for a couple of reasons. One is we sometimes have components in our irrigation system, gaskets, that type of thing, which will disintegrate, sometimes emitters. For example, even the little flaps you have in PC emitters. They can get degraded with a lot of chlorine. But what's less well understood is this idea about plant toxicity. And you can say, well, I have plants at home and my water's chlorinated. Yeah, sure, but that chlorination at home, you're down to like a half a part per million all the time. The plant toxicity depends on the specific plant. We don't know a whole lot about this, actually, surprisingly enough. But it can occur at 4 to 8 parts per million. And slug dosages are often in the 40 to 60 part per million range. So I would be very careful with slug dosages. if you have very clean water, sometimes you only have to apply the chlorine occasionally and just keep the bacteria population down. And I'm not talking about a slug dosage. I'm just talking about, you know, if you don't have much in the way of nutrition in the irrigation water coming in and it's very clean, it's one thing. If you have obviously dirty water, and which is the case in many situations, then you're down to continuous injection. But when you do inject, the thing is you want about a half to 1 part per million residual at the ends of the hoses, and you can buy little swimming pool test kits. By the way, swimming pool test kits test for 2 things. It tests for this residual chlorine, and it tests for the pH. Bingo, why? Because the pH is important when you have swimming pools. The same thing here. But here's what the deal is. If you're going to end up with a half a part per million and the water's really dirty, sometimes you have to inject 4 parts per million up at the pump. So you're not really going for initially an injection rate. Well, you are going for an injection rate, but the problem is you have to go out and check the ends of your hoses to see what the concentration is there, and then go back up to the head of the field, up to your injection mechanism, and make appropriate adjustments. So you have to do this a number of times, get the hang of it, and then you get it dialed in right. So the rule is, here is, well, I don't know exactly what the rule is, except that what you do is you go to the ends of the hoses, and if they're clean, which obviously didn't happen with the right-hand picture, and see, what we do is we use little nylon socks, and we just shoot all the water from the end of the hose into the nylon sock and see what's there. And if you find out there's all sorts of bacteria, sludge that comes out, you say, well, looks like we're not injecting enough, either not frequently enough or at a high enough rate. So that's the way you do it. There is no universal answer to concentrations and frequency. As with everything, people come up with different ways to do things. There are other forms of chlorine, not chloride, that are used in some areas. There's chlorine dioxide, and it really works in a different manner. It actually oxidizes the bacteria and kills it, as opposed to poisoning it. And you can purchase chlorine dioxide as a gas, liquid or powder, but up in the Pacific Northwest, a fair number of people actually have generators, you might say. It's kind of like an SO2 generator, sulfur dioxide generator, where the product is sulfur dioxide. These are different, but out comes chlorine dioxide. And so they're set up on individual fields. There have been all types of things over the years. We've had hydrogen peroxide just by itself, and then here there's this peroxacidic acid. So it's this combination of acetic acid and something else here. And what you see on this particular label is, notice it's sold as 5.6% antimicrobial solution. And and you can see the ingredients there. It's a combination of a couple things, and they're sold and they're used successfully for microbial growth reduction. Acid by itself is sometimes used to kill bacteria, and it also prevents the precipitation of calcium and magnesium compounds in the drip system, you know, in the emitters. And what happens there often is that you shut off your system, and the water's still sitting in the emitters, for example, and then you get evaporation, and the calcium tends to then precipitate out. And there are 4 common acids used. One is sulfuric acid, and that was discussed in some detail in the safety module, in other modules, other videos. Phosphoric acid, it's expensive, so it's not used too much. Urea sulfuric, N-furic it's called, and similar fertilizers. They're used both as a fertilizer and as an acid source. And then sulfurous acid, which was discussed in the SO2 video module. The thing about this is be careful with the acid because it's real easy to acidify a soil. And remember, sands acidify really quickly. And then on the other hand, we have some soils with a lot of free lime and they're not going to acidify anytime soon. But if you have a situation where you drop the pH, it may be difficult to bring it back up again. And so have some caution there. In other words, what this says is that you should be checking your soil pH along with your water pH and water quality. In other words, you should be doing more than just injecting water and fertilizer. Here's an SO2 generator in real-time action on a reservoir, and remember, you don't use this in conjunction with chlorine because they counteract each other. In fact, we use SO2 sometimes in city water treatment plants actually it's the sewage treatment plants for recycled water. We use SO2 to get rid of excess chlorine. How's that? So that's not something that would be too smart to do in ag. SO2 is used by itself often to kill slimy and iron bacteria, and also to prevent calcium precipitation and to burn out the bicarbonates. You know, any acid would do that, of course. So that's an infiltration problem thing. Now there's a whole group of chemicals that are sold for problems with minerals like calcium and magnesium precipitation. And some are called long chain linear polyphosphates. There was years ago there used to be something called Calgon that people would use, calcium be gone. That's where it came from. And it was a shorter chain linear polyphosphate. If that means anything to you, you can look it up in a book and learn all about it. The problem we have on the university level is that, yeah, we know that some of these work quite well. We know that some of them are real specific. They tend to really isolate iron, and they take the iron right out through the system, and it never is used by the iron bacteria. Or they may be very good with calcium. They may be very specific, but the problem is it depends on the formula and how these things are made, and we don't know. That information is all proprietary. So we can look at the claims, but it's very expensive to actually prove this. For example, our center, we're funded by contracts, and the outfits that make these things, they don't typically pay for tests, and you'd have to have a whole variety of tests, and it's not cheap, in other words, to test these things out. So we can't really tell you that, just in general, these things work great. We can say that, some of them work really well, but I don't know about your situation. Now, sometimes you get in a bind. In other words, something happens and you just go out there and you just have tremendous bacterial plugging, or maybe you want to fry some roots that got in. That's a little tough, but whatever it is, you're in a tough situation, and it's kind of like you're going to lose a lot if you don't try something. So you say, well, I've just got a shock, put in a high pH, really put a lot of acid in, or chlorine or something else. And so you say, gee, but I know that can hurt things. So let's take a look at how to deal with that. The problem is not that it takes a long time to get to the front of a hose. It doesn't take much time. When you start injecting something, it gets to the head of a hose pretty fast. But it takes a whole lot longer to get to the end of the hose. So meanwhile, while you're injecting this chemical at the head of the hose, there's this chemical going out of the emitters, and it's in this real high concentration. It's taking sometimes hours to get to the end of the hose. So you're quite likely to sort of fry your crop up at the head of the hose, and often the problems with the plugging are at the tail end of the hose. So let's take a look at this graph. On the horizontal axis, there you have tape length. So this was run with tapes. And you know, you have different sizes of tapes and different lengths of tapes. And so what we have here, it's a little difficult to see the fourth one, but you can clearly see 3 tapes. There's a green one that's on the top. And what you can see is, let's see, that's 1.37 inch tape. Boy, that's a big tape. And it has a real low flow rate, 0.22. Not real low, but 0.22 gallons per minute per 100 feet. Let's just look at that one first. So that's a real big tape. It takes a lot of water just to fill the tape up, and basically the water's not zipping along in it. And take the extreme case there, 1,200, 1,300 feet, something like that. You know, it's not quite 13, well, about 30, let's say a quarter of a mile. That's on the far right-hand side. If you started injecting a chemical into the head of that hose, in other words, the chemical finally arrived at that hose or that tape. Let's look over on the vertical side there. It's about 270 minutes before that chemical is going to reach the end of the hose. Well, ladies and gentlemen, that's a long time. That's a long time. So the longer the hose, the longer time it's going to take to get there. But nevertheless, even if you have a short hose, look at 200-foot length of that. It's going to take 200 minutes. That's over 3 hours to get to the end of that hose. And so that doesn't look really healthy. And then if you have smaller tape, and you know, this just gives you a little idea. Low flow again, that's the kind of magenta color there, kind of the purple reddish. You see it's a smaller tape, so it doesn't take as long, but nevertheless, if you're having a real high dosage, it's quite a while. So you can basically, whereas you're just trying to get the chemical to the emitters, maybe, and shut it off and let it do its thing for a while, then flush it out, it takes forever to get the chemical to the last emitters. So this deals with the shock treatment. You know, again, what if you just get stuck? And that happens sometimes. And things are really plugged up badly, and you have to put in some kind of a shock treatment, and it may even be that or lose the crop. But you don't want to use too much chemical. You know that's bad. You know having everything plugged is bad. So what's the compromise here? So here's how you do it, and I'll kind of go through this slowly and read it here. First thing is, the idea is you'll inject a chemical, but only inject it into a relatively small area of the field at once. And hopefully that'll become a little more obvious here. Before you start to inject, what you do is turn on the system, and you just don't have everything going though. Don't have all the hoses going. Turn on the system and first flush the manifolds. And you concentrate the flow, in other words, in a few manifolds, and that gives you a higher pressure there and high flushing velocities. Just so you know, a lot of the pipes have been reduced in diameter a little bit too much, and the water goes shooting out of the end caps or the end valves or whatever they have, and it looks like there's a high flow. All there is a high velocity, and it isn't really giving much of a velocity in the bigger pipes that are upstream. So you need to force the water through. So you've turned on part of the system, you've shut off the hoses, you've flushed the manifolds, and you meticulously go through the area and do this. So when you're done with that, before you do anything else, you turn off your pump, but then you close the manifold, flush out valves. Then what you do is open the hoses in a small area. A small area meaning if you have normally irrigate 60 acres at once, you would open maybe 20 acres at once. So maybe a third of the area. So that's all you do at once, and then you flush out as much of the contaminant as possible, simply because why in the world would you want to waste your chemical on contaminant that you can get rid of? So the pump is on, the hoses are open, you're flushing out water and dirt, and now you leave those hoses open, and believe it or not, you start injecting at the desired concentration, this high concentration, and you leave the hose ends open, and here's what's going to happen. The pressure in the hoses won't get very high, and so because the hose ends are open, and so instead of having a lot of the water go out through the emitters and chemical go out through the emitters en route to the end, it's just tooting along down the hose, and it'll get down there relatively quickly. And so once the chemical reaches the ends of the hoses, what you do is you shut the system down. Now, if you're doing acid, that's pretty easy to do. You go out there with a pH indicator, and when the pH suddenly drops, you say, well, chemicals reached here, So what that is once you notice that, you close off the hose ends, and now this chemical is pretty evenly distributed throughout the whole hose and all the emitters. Of course, there are multiple hoses. And then you go up and you shut the system down and let things bubble around. In other words, let the concentrated chemical work. So basically, here's what it is. You're getting the chemical down there relatively quickly, and then once that high concentration is there, you let it sit rather than continuing to inject. And so you flushed out the contaminants, you get down a small fraction of the time, you have a fairly uniform contact time if you're using chlorine, for example, throughout the system. And then you may have to repeat this process several times. In other words, you let it bubble around a bit, then you go through this whole process a few times, but you'll use much less chemical. And then there's the big deal of root intrusion. Roots go into the emitters from the emitter outlet. And certainly it happens a fair amount on SDI, subsurface drip irrigation. No, you cannot dissolve them. I've seen people try to do that with acid. And here's what I suggest. If you really think that's going to work, why don't you get some of this hose or tape, whatever it is, with roots in it, and just put some acid on it and see how well it works. And my guess is what you'll see is it doesn't work too well in terms of dissolving the roots. So really, it's just bad news if you have root intrusion. And so what do? A typical cause of root intrusion is what I've seen over the years. It happens a fair amount. It's almost always associated with under irrigation. And under irrigation can be two different ways. One is, believe it or not here, you can have localized under irrigation around an emitter if an emitter is partly plugged. So what's this say? You want to reduce root intrusion? Make sure your emitters stay clean. And that's from the inside out. Keep them clean, don't under irrigate, and you can drastically reduce root intrusion. That, ladies and gentlemen, is the module or video number 17 of our series, sponsored by CDFA FRET.